The last of the methods, the power series method, or basically the power series method, the third of the methods that we have for the inverse Z transform. Okay, so power series method. Actually, this is probably the easiest of the power series method, and you will find that it is almost straightforward for us to utilize this in a number of examples. Okay, so what we are saying is that the Z transform can be viewed as a Laurent series. Laurent series, which is in the study of complex variables, you will come across Maclaurin series, Laurent series. This basically, so if you are able to take the expression for x of z and write the Laurent series, basically, so what we are saying is whatever you have as a Z transform, you convert it into a Laurent series where you have the as a polynomial in terms of the powers of Z. Okay, so a Laurent series will be a polynomial. Okay, in Z. Okay, let's take a quick example of this. 1 over 1 minus Z inverse the whole squared. Okay, now where does this come from? Supposing you had a function 1 over 1 minus x the whole squared, and I asked you to do a Laurent series expansion, you would say that this will be equal to 1 plus 2x plus 3x squared and so on. So basically this is what will be given as the expansion, series expansion. So if it is now written as 1 over 1 minus z inverse the whole squared, this is equal to 1 plus 2 z inverse plus 3 z minus 2 and so on. So this corresponds to a sequence whose first term is 1, 2, 3, 4 and so on, and this is the origin. Okay, and it is zeros to the left of it. This is the sequence. Basically from the Laurent series we come to the conclusion that the corresponding sequence is 1, 2, 3, 4. Okay, now is that correct? Let's go back and look at this one. 1 over 1 minus z inverse, that is the Z transform of the unit step function. Okay, so 1 over 1 minus Z inverse the whole squared, multiplication of the Z transforms, means that I have convolved u of n with u of n. Okay, you have the unit step function, you time reverse it, and then as you slide along, it will become 1, 2, 3, 4, it will keep increasing all the way. So basically, this is what we call as the ramp function, right? We call it as a ramp function, but at the end of the day, it is u of n convolved with u of n, which has got a relationship, which is 1 over 1 minus z squared. Okay, so you can see how the Laurent series is just available for us to use as a general expression, which can then be leveraged to get the corresponding time domain sequence. Now apply this particular result. Okay, so here is an example for you to think about. If I told you that x of z equal to z inverse divided by 1 minus z inverse whole squared. Okay, what is the corresponding sequence? Since I know that the original sequence is given in this form, so it will be 0, 1, 2 and so on. this becomes my origin. Okay, and so basically it is a shifted sequence. So if this is n times u of n, then what we get here is this will be n minus 1 times u of n minus 1. Okay, is that correct? I have n times u of n, z inverse n minus 1 times yes. So basically what we will get is n minus 1 is 0 minus 1. No, it starts at n equal to 1. N equal to 1 is where it starts. So the first term will be 0. Then okay, yeah, this will work out. Yeah. So you can basically use the Laurent series if you have to shift it to the right by multiplying by z inverse, because z inverse times 1 minus z inverse the whole squared will be equal to, start with z inverse, 2 times z minus 2 plus 3 times z minus 3 and so on. So basically the whole sequence shifted to the right by 1 unit of time. So again, you can use the properties of shifting and also the Laurent series in a very powerful way. Now occasionally you will run into certain sequences which are not easy to work with. So for example, if I have h of z equal to logarithm, natural logarithm of 1 plus a z inverse. Okay, there is a operation where we take the logarithm of a transfer function, in which case you will get ln of these first order terms. Okay, if you get like this, how do we get the corresponding time domain sequence? Not a problem. Laurent series is available for us, saying that ln of 1 plus x can be written as x minus x squared by 2 plus x cubed by 3 minus x power 4 by 4 and so on. So basically it's the powers are increasing, the denominator is increasing and the sign is alternating. Okay, so then what we get is ln of 1 plus a z inverse. If you use the same formula, then this will be a times z inverse minus a squared by 2 z power minus 2 plus a cubed by 3 z power minus 3 and so on, dot dot dot. Okay, the sequence itself is a minus a squared by 2, a cubed by 3 minus a power 4 by 4. We have obtained the sequence. The general form, if you want to write down, it is x of n is equal to minus 1 raised to the power n minus 1 a power n by n u of n minus 1. It starts with n equal to 1. If it starts with n equal to 1, you get a power 1 divided by 1, that is a, and the corresponding sign will be plus, and then the next one will be a squared by 2 with a negative sign, then you'll get a cubed by 3 with the, so basically this is the general form. So how we can use the power series expansion for computing the inverse Z transform. And one of the very common tools that we have is to get the power series not by Laurent series expansion but by very simple long division. Okay, so power series obtained via long division. Okay, and it's actually a very simple method which is quite powerful. You can use it to obtain even when you have large polynomials. Okay, let me just use it, demonstrate it to you for very simple first order polynomial. Okay, if I have x of z equal to 1 over 1 minus a z inverse. Okay, how will I get the causal sequence? if I want to obtain, because this, remember this transform you can get causal and anti-causal. So if mod z greater than a, then you are looking for a causal sequence. In the causal sequence, what you write is decreasing powers of z, 1 minus a z inverse. What is 1 here? So when you do the long division, this first step is 1, then you get minus a z inverse, you subtract, this becomes a z inverse. The next step will be plus a z inverse, this will be plus a z inverse minus a squared z minus 2. Subtract this, these two terms will cancel, you will get plus a squared z power minus 2, then you will get a squared z power minus 2, and so on. You can see how the sequence is emerging. Okay, so this through the long division, what we get is this equal to 1 plus a z inverse plus a squared z power minus 2, and so on, which means that the sequence is 1 a squared and so on, which is the same as a power n u of n. Okay, so long division, look at the polynomial that you get as the division of the numerator by the denominator, and you will get this particular expression. The last one. So x of z equal to 1 over 1 minus a z inverse mod z less than a. Okay, remember last time we wrote it in decreasing powers of z. Now write it as increasing powers of z. Minus a z inverse plus 1. Z power minus 1, z power 0, increasing powers of z. Numerator also should be written in increasing powers of z. Here we have only one term equal to 1. So now if you look at this, what you get? Minus 1 over a z. Right? That is what will give you a 1, and then the next term will be minus 1 by a z. Okay, so now subtract, these two terms will cancel, you will get 1 over a z. Okay, now how do I get this from here? Minus 1 by a squared z squared. So then I will get plus 1 by a z minus 1 by a squared z squared. Subtract, these two will cancel, and you start getting the sequence, and the sequence will be minus 1 by a minus 1 by a squared, and so the sequence that is going to be produced is, this is x of n is equal to minus a power n u of minus n minus 1. Okay, why is it negative powers of z? So basically if you were to write this as a sequence, then it will be minus 1 by a 0 0 0 minus 1 by a squared, because that is the power of z squared, minus 1 by a cubed dot dot dot. Okay, this is the origin. Okay, that is a sequence. So therefore you get the corresponding sequence minus a power n u of. All right, so where are we? We have looked at the three methods of obtaining the inverse Z transform. One is by inspection, looking at the table and looking at the mapping. Second one is when you have a polynomial, write it in terms of partial fraction expansion. We looked at it when you had the unique roots, distinct roots, or you have repeated roots, doesn't matter. We can still use the same way. All you need to do is get those coefficients. Once you get the coefficients, you can look at the table and then obtain the inverse Z transform. And so this is a good place for us to sort of stop and say that we have looked at the complete picture of the Z transform. We have looked at it and understood that it's a powerful transform, in fact more powerful than the discrete time Fourier transform, because it exists even where DTFT does not exist, and it gives us several important tools which we can use in the study of the LTI systems. So we will now go on to looking at the material in chapter 5. We will give you an introduction to it and start with that in the next session, where we are looking at transform analysis of LTI systems using DTFT, using the Z transform. Okay, we will stop here. Thank you.